Section 20.4 Electronic Spectra of Complexes. Subsection A Ligand-Field Transitions. Let's look at this example. This is hexaamine chromium 3. This is because the oxidation number of one ammonia molecule is exactly 0, and overall there's 3 plus charge. That's just on chromium. Therefore, the oxidation number for chromium is 3. This is a D3 transition metal complex because the electron configuration of a chromium atom is 4s2, 3d4. But in a transition metal complex, you need to give all those 4s electrons to the 3d orbitals. So a neutral chromium atom in a transition metal complex is considered having 6d electrons. Now there's a 3 plus charge. That means this chromium has 3d electrons. And it's pretty easy for us to assign this 2 electrons, this 3 electrons, into the dxy, dyz, and dzx orbitals because they are triply degenerate T2G orbitals, which has lower energy than the EG orbitals in an octahedral complex. And delta O is roughly 25,000 wave numbers. 1 reciprocal centimeter is also known as just 1 wave number by convention. And again, this tells us the energy difference between the T2G orbitals and the EG orbitals is hc times this number. Well, h is the Planck constant, c is the speed of light, and then times this number. You may have to convert this number to reciprocal meters. All right, 2 reciprocal meters. If you do that, I think it's going to be 2.5 million reciprocal meters. So you need to multiply this number by 100 to get the wave numbers in reciprocal meters. But actually, if you take the UV-vis spectrum of this transition metal complex, you will see there are actually 2 corresponding electronic transitions. Their energies correspond to these 2 numbers, 21,550 and 28,500. So these 2 numbers are close to 25,000. But first, why there are 2 different transitions, and 2, why this one is lower than this and this one is higher than this. So now let's look at the electronic transition that takes place in this transition metal. When we promote one electron from one of the T2G orbitals to one of the EG orbitals, there are actually 6 possible options. Why 6 options? Well, you have 3 options here. You can promote one of the 3 electrons, each occupying one of these 3 orbitals. All right, so you can promote the dxy electron, or dyz electron, or dzx electron. 3 options. And after you promote this electron, you need to put it in one of the 2 EG orbitals, right? dz squared or dx squared minus y squared. So you have 2 options for the destination of the promoted electron. That's why there are a total of 6 possible transitions. This is the initial state. We have 3 electrons, each in one of the 3 T2G orbitals. This is the final electronic state. Now we have only 2 electrons in the T2G orbitals and 1 electron after being promoted in one of the 2 EG orbitals. So 6 options. And also we can look at the symmetry of the total wave function of all 3 electrons. So when you look at this lowercase t2g, that gives you the symmetry of individual electron. And then this 4a to g give you the symmetry of all 3 electrons in total. A is symmetric. Actually, if you think about this, you have 3 electrons in dxy, dyz, dzx. The wave functions are proportional to xy, yz, and zx. and the electron density is proportional to the wave function squared, and therefore proportional to x squared y squared, and y squared z squared, and over here z squared x squared. And then you sum it up, you get the electron density of these 3 electrons. You have x squared y squared plus y squared z squared plus z squared x squared. And actually that's symmetric with respect to x, y, and z. Therefore, it's asymmetry there. And for d electrons, we have a G symmetry label because if you look at any d orbital, it's symmetric with respect to inversion center. And if you look at this number 4, this is spin multiplicity. Based on Hund's rule, we know the 3 electrons should have the same spin. For convenience, we'll just say, well, they have alpha spin. Well, you can say they have beta spin as well, but let's just say all 3 electrons have alpha spin, and that means the z component is 1/2 plus 1/2 plus 1/2. You get 3 halves in total, and that's going to be the sum of the z components of the electron spin of the 3 electrons. And from that number, 3 halves, you know the uppercase M sub s can be as large as 3 halves. That means S, the total electron spin of the 3 electrons, is 3 halves. And the multiplicity, the spin multiplicity, is 2s plus 1. So 2 times 3 halves plus 1 is 4. That's why you have a quartet electronic spin multiplicity here. Now let's do the transition. Make sure you keep all 3 electrons with alpha spin. Otherwise, it's going to be spin forbidden. We'll talk about that later. You do not flip the spin of the electron in a electronic transition. Again, I mean, this is just to reserve the angular momentum for electron spin motion. Now let's look at the transition. You promote one of the electrons from the T2G orbitals to one of the 2 EG orbitals. And then you get this electron configuration right here. But then if you look at all 3 electrons in total in this transition metal complex, in this excited state, we have 2 symmetry symbols for the total wave function of the 3 electrons. Okay, all 3 considered together. It splits into 4 T1G and 4 T2G. And again, this 4 is the spin multiplicity. You still have the 3 alpha electrons, and T means triply degenerate. And G means Garroter with respect to inversion. All right, 1 and 2 are referring to symmetric versus antisymmetric with respect to rotation. We'll talk about this later. Now let's look at the initial orbital of the promoted electron, dxy, dyz, or dzx. And then let's look at the orbital occupied by this promoted electron. It could be dz squared. It could be dx squared minus y squared. So now let's look at this table. Again, we mentioned there are 2 different transition energies. Okay, so this is smaller transition energy. This is large transition energy. That means this excited state has lower energy than this excited state. How come? Let's look at this row. In this row, I'm just showing you a dxy orbital is replaced with dx squared minus y squared orbital. Over here, dyz is replaced with dz squared. Over here, dzx is replaced with dz squared. So if you look at this 3D orbitals in the bold font, they are just the EG orbitals. Also, we can do transition this way. Okay, over here, dxy is not replaced by dx squared minus y squared. It's replaced by dz squared. Over here, dyz is not replaced by dz squared. It's replaced by dxy squared, dx squared minus y squared. Over here, dxz is not replaced by dz squared in the top row. Over here in the bottom row, it's replaced by dx squared minus y squared. So really, if you look at here, dxy, dyz, dzx is replaced. Over here, dxy, dyz, and dzx is replaced. It's just we have 2 options where this electron goes. It can go to here or here, here or here, here or here. Now let's look at this situations. Let's compare this two, and let's compare this two. Let's compare this two. What's going on here? First, this is probably easy to look at. You know, dx squared minus y squared is on the xy plane, right? dxy is on the xy plane, right? So physically or spatially, these two orbitals are really close to each other, right? These two. Now, if you look at this situation, I mean, you can say dz squared, dxy, and dyz are on the same plane, but they have different orientations. There's an angle, 45 degrees angle between these two, and these two are just perpendicular to each other. These two are perpendicular to each other. So let's look at the orbitals. dx squared minus y squared. Look at this two. They are both on the xy plane. So I want you to imagine plotting this x squared minus y squared here. So you'll have one lobe here, one lobe here, one lobe here, one lobe here. I know there's a 45 degrees angle between dxy and dx squared minus y squared because again, I mean, over here the nodal surface is corresponding to x equals 0, y equals 0. Over here, it's x equals y, or x equals negative y. So there's a 45 degrees angle, but these two orbitals are on the same plane. And if I draw the four lobes of dx squared minus y squared here, these four lobes and these four lobes are awfully close to each other. There's strong repulsion. If you put one electron here and one electron here, these two electrons will strongly repel each other just because they are close to each other in space. Okay, so that's why you have large repulsion between this orbital and this orbital. Okay, that's why this excited state has higher energy than this excited state. I did mention that dz squared and dyz are considered on the same plane. So this is dz squared, this is dyz. So you can plot dz squared here, one lobe here, one lobe here, right? One lobe here, one lobe here. And it's true that this lobe is close to these two lobes. This lobe is close to these two lobes. And this ring over here is, I wouldn't say as close as between these two lobes and those four lobes. So yes, indeed, this two has also some repulsion, but not as strong as the repulsion between these two orbitals. So again, these two repel each other more strongly than between these two. All right, so this two has really little repulsion, stronger between these two, but these two are the strongest. So that's why the repulsion between this one and this one is stronger than between this one and this one. All right, and then we look at this column. Similar analysis. These two are on the same plane, xy plane. They strongly repel each other. All right, dz squared and dzx also repel each other, but not as strong as between these two. And over here, dx squared minus y squared is perpendicular to dyz. It's perpendicular to dzx, and these two are perpendicular to each other. So now the three orbitals are in the same plane. So there's very little repulsion among these three d orbitals. However, if you look at this situation, dz squared and dyz are on the same plane, you know, partially, right? So these two lobes, this lobe is really close to these two lobes. This lobe on the bottom is really close to these two lobes. So again, there's more repulsion between these two, and also there's more repulsion between these two than between any two of those. dz squared, dxz, this lobe is physically close to this two. This lobe is physically to this two. So again, that's why you need to look at the shapes of the d orbitals and realize that if the lobes of two orbitals, two d orbitals, are close to each other, closer to each other, you have stronger repulsion. And this is why you have two electronic transition energy. Again, because you can promote Y electron from the T2G orbitals to the EG orbitals. There are 6 options. 3 of them are grouped into this 4T2G symmetry. The other 4 is grouped into this 4T1G symmetry. They have the same spin multiplicity. They are the same as the spin multiplicity of the ground state. But over here, this 2G, this 1G, they do differ actually in symmetry due to the different symmetry between dz squared and dx squared minus y squared. Right? And I mean, if you can just imagine, if you put this dz squared orbital in the z direction and you rotate it 90 degrees, there's no change to this. However, if you rotate dx squared minus y squared, alright, there's going to be a sign change. When you rotate d squared minus y squared about the z-axis 90 degrees, you're going to change the sign of the wave function of dx squared minus y squared. Alright, so the difference between the symmetries of these two causes the difference between the symmetry labeled here 2 and 1. Alright, let's look at the shapes of the orbitals again, because I want you to remember. You need to examine the physical distance between the lobes of 2d orbitals and then decide which 2d orbitals have stronger repulsion than some other 2d orbitals. And again, these 2d orbitals, dxy and dx squared minus y squared, repel each other more strongly than any other 2d orbitals, because they are on the same plane, and these 4 lobes are awfully close to these 4 lobes. Now let me give you a few other examples, and all of them are chromium-3 complexes. So they are bonded to 6 fluoridyl ligands, or you can say 6 fluoro ligands. Fluoro is the common name, fluoridyl is the UPAC name. 6 aqua ligands, 6 amine ligands, double M, AMMINE, double M, 6 cyanidyl ligands. Alright? And pay attention to the charges. This is because over here you have F minus, you have Cn minus here. And this aqua ligand and this amine ligand are neutral. So that's why you have 3 minus here, 3 minus here, 3 plus here, 3 plus here. So in all 4 cases, chromium has an oxidation number of 3. Now let's look at their electronic transition energies. Well, in each case, you have 2 different electronic transition energies. Those are also in wave numbers. Again, one wave number is just 1 reciprocal centimeter by convention. I think there's a historical reason for this. Why we use reciprocal centimeter instead of reciprocal meter. I think in the old days, people don't care about using SI units or even use consistent units. All right, and also when you take infrared, when you take an infrared spectrum of an organic compound, you'll see the range is usually between 400 wave numbers to 4,000 wave numbers, where each wave number is 1 reciprocal centimeter. I think there's, again, historical reason for this, for using a non-SI unit here. Now let's look at those numbers. Well, of course, I mean, they are different, and then we can take the average. The average is actually the delta O, the crystal field splitting parameter, delta O, for this octahedral complex. Look at the delta O's. And then we can take the difference. The difference originates from the difference in the electron-electron repulsion. All right? So now let's look at the average first. 19K, 21K, 25K, 29K. You can see all these numbers are in the increasing order. Look at this ligands. Weak field ligand, relatively weak. In the middle, over here, strong field ligand, because cyanide is a pi acceptor. Ammonia is neither a pi acceptor or donor. Water is a very, very weak pi donor. All right, so water has 2 lone pair electrons. It will use 1 lone pair to form the sigma bond. The other lone pair can be donated to a empty d orbital centered on chromium, but the orientation is not right. The orientation is roughly 109 degrees. It's not a perfect 90 degrees. It also, oxygen usually does not like to give away electrons because of its high electronegativity. And fluorine, fluorine is a fluorine has 4 lone pairs. So 1 lone pair is used to form a sigma bond between chlorine and fluorine, between the chromium transition metal center and the fluorido ligand. And then fluorine has 3 other lone pairs potentially can be used to be donated to a empty d orbital centered on chromium. So actually fluorido has a stronger ability than water in donating their lone pair electrons to an empty d orbital. So fluorido is a even weaker field ligand. And that's why we see the trend here: 19K, 21K, 25K, 30K. And I think I explained this. Delta O. When you have a strong field ligand, it's roughly 30K. When you have a very weak field ligand, it's roughly 10K. In the middle, it's 20K. So if you look at these 4 numbers, it's slightly higher than the range I mentioned. I think it's because we're looking at a chromium 3+ with a oxidation number of 3. If you look at 3D transition metals with an oxidation number of 2, I think the numbers will match with the 10K, 20K, 30K range better. So these 4 numbers are slightly higher than the range I mentioned above. So ammonia is supposed to be in the middle. It's supposed to be around 20K. It's 25K, slightly higher. I think if you have chromium 2+ here, it's going to be closer to 20K. And another reason this is quite above 10K is because this is not the weakest field ligand. I think the weakest field ligand in common spectral chemical series of the ligands are ardido and bromido, I think. They actually can better donate their lone pair electrons to the transition metal center. So that's one reason. Another reason, of course, is this oxidation number of 3 is larger than 2. All right, and then let's look at the difference. The difference is actually the difference between this 4T1G and 4T2G. The difference is roughly, if you look at this, roughly 7K wave numbers. 7K wave numbers is a little bit lower than 1 electron volt. 1 electron volt is roughly 96 kilojoule per mole. So I'm going to say, well, the difference is roughly 80 kilojoule per mole here. Okay, the difference between 4T1G and 4T2G. All right. Finally, I want to remind you again. This 4T2G and 4T1G have different energies because of the spatial distribution of the electrons. All right? And I want you actually to focus on the repulsion between dx squared minus y squared and dxy, because this is the most obvious strong repulsion case. So these two are on the same plane. And the 4 lobes of here and the 4 lobes of here, actually, you should plot them in the same picture, and these 4 are here. And that's a very close relationship between dxy and dx squared minus y squared.